Alright, so again, we're continuing with this. Continuing again with the Enols, the Enolates. So what did we say about the Enols and the Enolates?
Like in what?
Like or what are they?
They, like, you make them so they can like attack, like nucleophiles.
Perfect. So first of all, we're going to be generating these guys from aldehydes and ketones. Right? So we're going to be generating these guys from. Now, in particular, we can also generate. We can generate enolates. Well, actually, we can also generate. You can kind of see it as both too, if it occurs in acidic. So we'll just also add esters here too. Right. Now, what did we say that these guys? What are they going to function as?
Nucleophiles.
Yeah. Okay. The function is nucleophiles. So now notice that what we're seeing here is that we have an aldehyde or ketone or an ester. We can generate enols and enolates. Then those enols or the enolates or whatever we generate here, we can interpret them as functioning as a nucleophile. Now, if we have a nucleophile, then if we have an electrophile, what should occur?
Sorry, what?
If we have a nucleophile and an electrophile, what will occur?
It'll attack the electrophile.
Perfect. So now, because they can function as a nucleophile, then they can react with electrophiles. So what we're going to be seeing is, first of all, how do we generate these enols and these enolates? Well, we're going to be starting off with aldehydes and ketones and the Aldol reactions. So in the beginning of this unit, you're going to be generating the enols and the enolates starting with aldehydes and ketones. And you're going to be doing that by using acid or base. To generate the enolates, we use base. To generate the enols, we use acid. And we'll get into that. Once we generate either one of these guys, they will now function as a nucleophile. And because they are functioning as a nucleophile, we can react them with a lot of different electrophiles. And this is where most if not all the reactions that you're going to see is coming from. Because we've generated this nucleophile now we can react it. And we can react it with so many different things. And so we have, that's why you see all these different reactions. Right, okay. So, all right, let's start. Okay, so now this is saying aldol cross condensation reaction. So we're starting off with this molecule here, right? And we're reacting it with LDA. And so reacting this LDA, and the structure of this LDA this is how that LDA will look like. LDA is a powerful base. Alright. Now, what we're going to say here is that we're going to be producing these enols and these enolates by reacting these aldehydes, these ketones with acid or base. If we're dealing with base, we generate enolates. If we're dealing with acid, we generate enols, right? Because it all is like alcohol, right? And the only way we can produce an alcohol is if we have a proton on there. This is OH, right? Okay, so now if this is a base, then we're going to generate an enolate, right? We're starting off with here with a ketone, right? So a ketone is able to generate an enolate in basic conditions, and the way that this is going to occur, right, is that we're going to have some alpha hydrogens, right? So I showed them in red here, right? And this base is just gonna go ahead. It's gonna go ahead and take one of these guys. And as a consequence of that, we're gonna generate this, right? Now this here is going to have a resonance structure. The electron can go here and back here. Okay. And we can have this. And this is my enolate. Okay. So what we're saying is if we start off with aldehydes and ketones or esters, in this case we're looking at a ketone, but if we start off with any of these guys, we can generate enols or enolates, right? We generate the enols in acidic condition, we generate the enolates in basic conditions. We just started off with a ketone here, reacted it with a powerful base, took off one of these alpha hydrogens, generated a negative charge here, has resonance. Both of these structures are my enolate. Now, because both of these structures are my enolates, what do they behave? Or my enolate? It's one compound, right? It's just resonance. What is the purpose of the enolate? What
A nucleophile. It's like an attack.
what will it be attacking?
Electrophile.
Okay. Now let's see what's going on here. So now, the next thing that's going to be occurring here is that we're going to react this with CH3I. And then under here, you're going to have an SN2 reaction occurring. Now notice that there's going to be a polarity here, right? And this is going to be partially positive, and this is partially negative. So this here should be my electrophile. Right? So I already got my nucleophile here. Right? And that's my electrophile. So then what should logically happen?
The enolate's gonna attack the CH3.
Perfect. So this electron, the way it happens is this electron comes back down, then this reaches out and grabs this and does an SN2 reaction and kicks off the leaving group. Cool. Then we have so that's what's occurring. And then this here that they showed is just another maybe a minor product, but this is the main thing they're concerned with this here. It's the main product. Does this make sense? So in this case here, we're just seeing this nucleophile reacting with an alkyl halide to generate this product, which is just a substitution of one of the hydrogens for the methyl group. Alright, so since this enolate is going to be functioning as a nucleophile, we can react it with another electrophile. Alright. Now we can react it with this electrophile here. In this case, what is this here? Okay. Enolate. What did we start off with?
Ketone.
Okay, and now we're reacting with aldehyde. That's an aldol reaction. But notice that before we could have done the aldol reaction, we must have first of all generated a nucleophile and then reacted it with an aldehyde. So now we're going to get an addition reaction occurring. And what's going to occur is that this is going to be our nucleophile, right? This is going to be our nucleophile. This nucleophile is going to insert itself here, right? Electron will swing up here, and this guy will get protonated. So it would just have this whole entire molecule. From here, it's just going to insert in here, like that. That's what's going to occur. So in the regular addition reaction, right? In the regular addition reaction, we started off with something like this. Reacted with a nucleophile, and it usually was an acid, but it can also occur in base. And we generated this. So what's going to occur in this reaction is that this here now is going to be my nucleophile, and it's just going to insert here, and this guy will get protonated, right? So we can work it out here, right? So we're going to start off with this here, right? And the nucleophile that we're using is this. So then our product should simply be now I'm going to call this 1, 2, 3, 4, 5, 6. I'll call this 1 because that's where it's going to be attached. Attach that 1, 2, 3, 4, 5, 6. In my 6th position, I have a carbonyl. So, and this is a hydrogen. This here, oh sorry, this is my addition product, right? But in this context, we're gonna call it our Aldol addition product. Does this make sense how we got the aldol addition product?
Yeah. How come with this, it's like he attacked like here? Like
so it's a little bit backwards because here it was supposed to be this being here and this nucleophile being here, right? So notice how we don't start off with the nucleophile. The nucleophile is on top of the arrow. But in this case here, this is the nucleophile, and then we're reacting with the aldehyde. So you have to have known that the aldehyde is what's reacting with the nucleophile.
So like this is coming in here, or no, this is coming in there.
That's right.
Okay.
And then we have this tetrahedral intermediate, then it gets protonated, just like what would normally happen.
Okay.
So you already know the aldol condensation. All it is nucleophile comes in here, this electron swings up here, negative charge here, and then we protonate it. And this is how we're landing on this aldol addition product. All right? So you can count the carbons, you see it's the same thing. And you could make it in a more linear form. Just like you could make it in a more linear form. You could have, made this a little bit more linear like that and put the OH on there. Makes it look nice. But that's the exact same thing as what you have. Right? Just looks a little bit different. But it's the exact same thing. Okay, so yeah, so that's what this is here. Now it turns out that this is not usually where you stop. Usually it's not where you stop. So let's look at the scheme, what we developed. If we start off with an aldehyde, or let's just say a ketone, since we started off with a ketone. We start off with a ketone, right? We can react it with a ketone. Or we can react it with an aldehyde because that's what we just did. Right? But this aldehyde must be first of all turned into a nucleophile. Alright, let's just say we react it with an enolate. Right? So we have a ketone, we can react it with an enolate. Now in the case that we just saw, the enolate was enolate came from an aldehyde. And how did we create the enolate from the aldehyde? We used LDA. We started with aldehyde, used LDA, created the enolate. Oh no, sorry, this is backwards. Sorry. We started with aldehyde.
Yeah,
let's try. That's an aldehyde here. Okay. It's a little bit harsh, but I'll get it. Okay, so aldehyde here is supposed to be a ketone here. So we had started off with a ketone, used LDA, created the enolate, and then reacted with an aldehyde. And then we generate our aldol addition product. Right? Okay, so it turns out that we don't always end here. We can go further to the condensation product. Right, this is what you're seeing here with these double bonds.
So like, would it ever stop just here, or does it always?
Yeah. So there are some conditions that would determine that. So if we're here, right? If you added heat, you would get here. Or if for stability reasons, let's say because of conjugation or whatever, you can favor it to form this condensation product. Yeah. Cool. So now looking at this here, all the condensation product is this OH here. We're gonna get it to leave. So we're gonna use another base, and we're gonna take this proton here, form a double bond here, and kick off this OH. So then we would form. I'm gonna turn the molecule around so it looks a bit better. This is going to be the condensation product.
So like what to the base use? Was it water? To like remove the H?
Yeah. Yeah, it was water that was used. And this is just showing you the different stereoisomers that we could form. So we could have also had formed so we could have also formed this. Yeah. So these are different stereoisomers. So this makes sense so far. All right. So we'll look at Aldol condensation. The purpose of the Aldol condensation, right, is to join two aldehydes or ketones, right? So let's look at the possibilities. Right? In the first case scenario, we can have an aldehyde trying to join to a ketone. Right? So this is the first case scenario. So the purpose of the Aldol condensation is to join aldehydes and ketones. Right? We're looking at just two molecules. We're not looking at like three, just two molecules. So the first possibility is that we can have one aldehyde and it's joining to a ketone. All right? The second case is that we can have an aldehyde trying to join up with an aldehyde. Right? What do you think the third case would be?
Ketone and a ketone.
That's right. Now, it turns out that before, so once if we join any of these guys here, we would first of all form so we're going to first of all form the Aldol addition product. Right, so that's what we would form. If we join any of these guys in each of these cases, we would form the Aldol addition product. Now it turns out that before we can join an aldehyde and a ketone, or aldehyde and an aldehyde, or a ketone and a ketone, one of them must be turned into a nucleophile. Alright? So one of these sections here it could be any one, it could even be this side. Must function as a nucleophile. Right?
Mm-hmm.
And then the other one must function as a target. The other one must function as a target. A target for that nucleophile. So then the nucleophile now will react with that target. And of course, that target must have an electrophilic center. Alright?
Okay.
So in this case, we're reacting a ketone and a ketone. So that's the aldol condensation. And so before we could have reacted it, we must first generate the nucleophile, which is our enolate, and react it with a ketone to generate this tetrahedral intermediate. Then we have we just protonate this guy here to generate